Hi, we're going to talk about diabetes, and we'll start out with some basic stuff, but we are going to get into some of the more advanced stuff. I mean, anybody can understand this if you just want to understand diabetes. So the first picture is just going to show electron transport on the inner mitochondrial membrane. We're going to work towards this, but this is what this talk is leading to, and we're going to go through a lot of interesting stuff about diabetes. The reversal of electron transport in the mitochondria is the key thing to insulin resistance and to diabetes complications. Okay, real quick, some background information. I realize much of the audience already knows all this stuff, but there's a surprisingly large number of people who do not know this about diabetes. So the first point is diabetes is caused by an excess of dietary fat. There are other things that contribute to insulin resistance: excessive stress, excessive dietary sodium, deficiency of dietary magnesium, but the most important thing is a high intake of dietary fat. Populations with high intakes of dietary fat have a lot of diabetes. Populations with low intakes of dietary fat, like 10% or less, have hardly any diabetes. Another question I thought was pretty interesting. Nathan Pritikin, he's not a doctor, but Nathan Pritikin, he's a genius. He's talking about there was an experiment where they tested the oral glucose tolerance test at 7 o'clock in the morning and at 7 o'clock at night. And what was interesting was lots of people were negative for diabetes on the oral glucose tolerance test done at 7 a.m. in the morning, but then they'd have a high-fat lunch and a high-fat dinner, and they would test positive at night. So Pritikin made the observation, gee, most Americans are probably diabetic if you just test their oral glucose tolerance test at night. So if somebody's eating a standard American diet, let's ballpark that at 40-45% fat, they're going to end up eventually testing positive for diabetes, because diabetes causes insulin resistance. High-fat diet causes increased insulin resistance. So these studies, I've got the references listed at the end of the paper if you're interested in them. But we've known since at least 1927. You can take a bunch of healthy people like medical students, feed them a high-fat diet, and they'll test positive for diabetes based on the oral glucose tolerance test. Feed them a low-fat diet, a carbohydrate diet, and they will not. Starvation will also cause a positive diabetes test because it'll increase blood lipids. When you're starving, you burn through your glycogen in the liver within 48 hours, and then the fat is going to release fat into the blood, and so the high blood fat's going to cause insulin resistance. And it's thought that happens because it therefore, by all the tissues of the body, as much as possible, burning fat, then whatever glucose is available can be prioritized for the brain. Okay, and lots of places, including Dr. Kempner's work, Nathan Pritikin's, Neil Bernard, the Mastering Diabetes guys, Bobby Bitteroo, Cyrus Kambata, they've all shown you put people on a plant-based diet, Dr. McDougall too, and that's low fat, and you'll more often than not, reverse type 2 diabetes. It's really a question of how soon you get to the patient, that they still have some intact insulin function in their pancreas. They haven't burned through all their beta cells. And it's also been shown when there has been rationing during World War II, World War I, and Cuba in the 1990s. Whenever there's rationing and people start eating less meat and less fatty foods, there's a reduction in diabetes. And the opposite is true, that whenever you westernize a country in the sense of eating more of a high-fat diet, as we've seen in China, Japan, Okinawa is part of Japan, there's much more diabetes. Okay, so basic summary of the sort of stages. I kind of made up these stages based on a lot of reading and studying, but they work. First of all, you get accumulation of fat in the skeletal muscle. That's the first detectable finding, like on nuclear magnetic resonance spectroscopy, is accumulation of fat in skeletal muscle. They'll call it intramyocellular lipids. So intra, within the cell, myo means muscle, lipid just means fat. And that causes inhibition of the insulin receptor. In a sense, the cell senses what one might call overnutrition. Don't bring in any more energy nutrients. After fat is accumulated in the skeletal muscle cell, it begins then to accumulate in the liver, and this causes insulin resistance in the liver. So the liver is similar to the skeletal muscle in that sense, that intracellular accumulation of lipid causes insulin resistance. And that's a very big deal because the liver is a center of metabolic headquarters to control blood glucose level. In particular, it maintains blood glucose level during fasting, between meals, overnight, while one is asleep. And when the liver becomes insulin resistant, then what happens is it's going to keep on running gluconeogenesis to produce more glucose and push it into the blood, even when it doesn't need to. And so you're going to have this chronic high blood glucose at all times, fasting. And when you get skeletal muscle insulin resistance, that's primarily postprandial hyperglycemia. liver insulin resistance, then it's fasting hyperglycemia as well. And eventually the fat starts accumulating in the pancreas, and that is damaging to the beta cells, which are the cells that make insulin. And then this then leads to a loss of beta cells and eventually a complete inability to make insulin. And the progression of the disease gets worse and worse. And as there's worsening hyperglycemia in the blood, elevated blood glucose, that then damages some key areas, the retina of the eyes. It also damages the mesangial cells, the glomerular macrophages. And it also damages peripheral nerves, and it also leads to thrombosis of small arteries, a lot of amputations in diabetics. So the sooner one can get the disease under control and minimize dietary fat, the better off the patient will be. We're going to talk a lot about the mechanisms of diabetic complications because it relates to causation as well. Okay, here's a great paper. This is one of the best papers, if not the best paper ever written on diabetes, called The Pathobiology of Diabetes Complications, a Unifying Mechanism. This was the Banting Lecture of 2004 by Michael Brownlee, PhD. This is a genius paper. It's one of the best papers I've ever read on, it's an incredible scientific paper. And there's a video of it available. You have to go to the diabetes.org website, but it is available to watch the video, which is extraordinary. He lectures and basically summarizes the paper there. It was published in 2005, even though it was the Banting Lecture of 2004. Okay, so what do we know about what causes insulin resistance? We know that excessive dietary fat leads to, and he's one of the main guys who figured this all out, Michael Brownlee, leads to an excess of electron carriers inside the mitochondria. And this then overwhelms the intermitochondrial membrane electron transport system, because when the gradient gets very high by pumping so many protons, we're going to see a picture of this in just a moment. When the protons are too high within the intramembranous space within the mitochondria, then complex 3 of the mitochondrial proton pumps can't pump against that gradient, and electron transport will reverse. Okay, and then this leads to the generation of free radicals like superoxide in particular, because coenzyme Q will drop an electron onto oxygen that then becomes a free radical, meaning that it has an unpaired electron in its outer shell, so it's hyperreactive, and it's like a super ball bouncing around indoors, damaging things. And then this also causes like a traffic jam, a backup of, because electron transport is reversed, that means Krebs cycle has nowhere to go, and that becomes reversed like a traffic jam, and so does glycolysis. We'll go through this all in a picture in just a moment. And what's the big lesson to learn? What's the key thing to get out of all of this? You want to really minimize your dietary fat. That's why you're going to hear people talking about, oh, good fats, this and that. You know what? I don't believe there's any good fats. And the reason I say that is, number one, high fat causes insulin resistance. Number two, high fat causes decreased oxygen supply to the tissues, hypoxia. And as Warburg has shown, if hypoxia gets up to 35%, then that has a tendency to induce cancer, okay? In addition, hypoxia related to fat plus just the effect of fat itself, as we're talking about here with regard to insulin resistance, causes mitochondrial dysfunction. Well, mitochondrial dysfunction is associated with accelerated aging. It's associated with cancer. It's associated with worsening atherosclerosis. There's nothing good about it. And it's not just saturated fat. This has also been seen in polyunsaturated fats, so all the different oils. You also get increased insulin resistance from omega-3s. Normally after eating, that's called postprandial, 80% of the ingested glucose goes to skeletal muscle, where it is stored primarily as glycogen. So the skeletal muscles are a good place to store that excess glucose right away. And then the liver also stores a lot of the glucose as glycogen as well. And it's going to use that then to maintain blood glucose overnight, along with gluconeogenesis, which is almost like a reversal of glycolysis. Oh, by the way, Nathan Pritikin had really studied the issue of how much fat there should be in the diet, and he came to the conclusion there's no such thing as a diet that's too low in fat. Any naturally occurring set of foods you could eat, you will get more than enough fat. And we talked about this in other lectures, like the lecture on omega-3s. There's a lot of omega-3s and omega-6s just in plant foods. You don't need, any special supplement or anything. Skeletal muscle uptake is insulin dependent. So that's another important point. You have to have insulin present to take glucose into the skeletal muscle. The one exception to that is if you exercise a lot, the exercise sort of overrides the system and also gets the glucose type 4 transporters up to the plasma cell membrane to allow glucose into the cell. But the key point about it is, regardless of what the blood glucose concentration is, the skeletal muscle is only going to take it up at rest if its insulin receptor is sensitive enough to do so. There's other cells of the body, though, that take up insulin based on whatever the blood glucose concentration is. And that ends up being a big deal because when you've got this insulin resistance, hyperglycemia, these cells cannot protect themselves. They cannot stop excessive glucose from coming into the cell. And when excessive glucose gets into the cell, so you have intracellular hyperglycemia, those cells will also be overwhelmed in terms of their too many electron carriers going to their electron transport chain. Basically the same thing as when you have excessive dietary fat. But excessive dietary fat is more dangerous, of course, because it gets into the skeletal muscle faster than does the glucose, and it just overwhelms the mitochondrial electron transport chain. And I believe, to me, it's pretty obvious from studying this and reading this, that our body's just not made to routinely eat excessive amounts of dietary fat, and our metabolic system just can't handle it. Our metabolic system is designed to handle starches and fruits. Okay, so the main locations that are damaged with diabetes-related hyperglycemia are the arterial endothelial cells, especially like in the retina, and that's a frightening thing because the retina is really part of the brain. So who knows what's going on in a lot of the brain areas, and we'll talk about that in some other lecture because that gets more complex. But there's a good reason why Alzheimer's is sometimes called type 3 diabetes. The next thing is mesangial cells, which is the residential macrophage equivalents in kidney glomeruli, which is the part of the kidney that filters the blood. And normally those macrophages remove debris from the extracellular matrix, means the space between cells. And so when those cells become dysfunctional, they can't clean out those spaces, and you just get all this crud accumulating that thickens the basement membrane, causing diabetic nephropathy. And the most common reason somebody ends up on dialysis is because of diabetes. Next most common will be hypertension. In addition, other cells that have a concentration, blood glucose concentration level dependent uptake rate of glucose into the cell are the peripheral nerve cells, and there's cells that myelinate them called Schwann cells, and that's why you get a peripheral neuropathy with diabetes. One thing though that's really key is if you improve oxygenation of those neurons, they'll often improve a lot. So a lot of diabetic neuropathy, it's not just the blood glucose level, it's a question of oxygen as well. Glycolysis, we talked about that, gets flooded by excessive glucose in the context of hyperglycemia, and then both fat metabolism and glucose metabolism have to run through the mitochondrial matrix. So they both then generate the same excessive amount of electron carriers. So once you get to Krebs cycle, whatever happens due to intracellular hyperglycemia and due to excessive intracellular fat, it's the same thing at that point. All right, so here's the beginning of glucose going into a cell. Glucose comes into a cell from the capillary. First thing that happens is it gets phosphorylated. That puts a big negative charge in there and traps it inside the cell. The enzyme is hexokinase, or 6-carbon sugar. I call it glucose because if you write it out in a Fischer projection, you know, the elongated stick form, then it's going to have an aldehyde on it. And that becomes helpful to remember that glyceraldehyde is the big molecule we're going to concentrate on. That's the most important molecule for purposes of understanding diabetes-related complications. And you don't need to know all these steps within glycolysis, but it's just helpful to have heard of them, have a general overview sense of them, because again, they're going to explain a lot of the complications of diabetes. Glucose 6-phosphate gets isomerized to fructose 6-phosphate, and then another phosphate's ended at PFK, phosphofructokinase. That's a major regulatory step. By the way, fructose, when it's metabolized de novo from dietary fructose, comes in just beyond this regulatory step right here at DHAP. And that's why it can just bypass glycolysis regulation. So, but going on with our glycolysis, glyceraldehyde 3-phosphate is the key location because this enzyme right here, glyceraldehyde 3-phosphate dehydrogenase, that's the one that gets inhibited. And when that's inhibited, everything before that is backed up. It's a major traffic jam in glycolysis. And then whenever you have a large accumulation of a substrate way beyond its normal amount, you start running these unusual side pathways. And those play a major role in insulin resistance and diabetes. Okay, so now we're going to talk about what starts to happen. Because you've got too much fat getting into the cell, it undergoes beta oxidation and it starts making these electron carriers. NADH and FADH2 are electron carriers. It's basically like reducing units. It's sort of the energy transfer systems of the cell. Normally what happens is NADH delivers electrons to complex 1. So these are the complexes of electron transport. And by the way, just to get orientated on the location, this is inside the mitochondria, the energy factory of human cells. The mitochondria has two membranes. There's the outer mitochondrial membrane. It's often abbreviated OMM. And then there's the inner mitochondrial membrane, often abbreviated IMM. So here I got it, IMM over here. And what happens is NADH gives its electrons to complex 1. Complex 1 then passes those electrons over to coenzyme Q. Complex 2 also picks up an electron, and it gets it from FADH2. The difference, though, is that complex 1 pumps out a proton into the intramembranous space. It's called intramembranous space because it's in between the outer mitochondrial membrane and the inner mitochondrial membrane. Complex 2 is really part of the Krebs cycle of reactions. Krebs, by the way, was one of the trainees. The guy who won a Nobel Prize. He was a trainee of Otto Warburg as well, as was Walter Kempner. Okay, anyways, complex 2 also gives its electrons to coenzyme Q. So coenzyme Q runs within the inner mitochondrial membrane, and it then delivers electrons to complex 3. Complex 3 normally pumps a proton out into the intramembranous space. Then it passes its electrons on to cytochrome C. Cytochrome C then passes its electron over to complex 4. Complex 4 uses the energy of electron transfer to pump out another proton, and to keep on building up that gradient of protons. In addition, we see here that oxygen, which has a very high electronegativity, means that it wants electrons. It really wants to pull on electrons. It will then obtain those electrons and become H2O, water, okay? And this is a key step right here. This is a really important thing. You have to have oxygen available in order to run this whole electron transport chain. All these complexes here are called the electron transport chain. And then the way energy is produced, ATP is produced, is that a proton at this protein here, transmembrane protein, is called ATP synthase, is allowed to re-enter the mitochondria. The center of the mitochondria is called the mitochondrial matrix. And the energy of entering along its concentration gradient and electrical gradient, it then enables this phosphate to be added to ADP and becomes ATP. ATP is the energy currency of a cell. It's like a $20 bill in a cell. Okay, and so that's electron transport, and this can make tons of ATP. If you just run anaerobic glycolysis, you only get 2 ATP per glucose. If you run it through electron transport like this, you can get about 36 ATP per molecule of glucose. So that's about 18 times more ATP production when you've got aerobic with oxygen metabolism. Now we're going to talk about what causes insulin resistance. When there's an excessive amount of fat within the mitochondrial matrix undergoing beta oxidation, it's going to be producing too many of these NADH and FADH2s. So coenzyme Q gets overwhelmed with too many electrons, and what ends up happening is so many protons are pumped into this intramembranous space that the gradient gets too high. It's hard to pump against a high gradient, and so complex 3 does not have the energy to pump against a higher gradient. There's a certain threshold, and this has been proven by Michael Brownlee's research. So what happens is the electrons start to go backwards, and coenzyme Q will now drop an electron, throw it down into the matrix, where it'll combine with oxygen to form a free radical. So a free radical means an unpaired electron in the outer shell, and that free radical of oxygen with a negative charge on it is called superoxide. Now, superoxide can be neutralized by SOD, superoxide dismutase, within the mitochondria. It contains manganese, but think of it as mitochondrial superoxide dismutase. And there's additional reactions, but the net result is the free radical is neutralized. It's not going to cause any damage if SOD can quickly get to it. It's a catalytic, very fast way to remove superoxides. But when there's an excessive amount of dietary fat, this process just overwhelms all the defensive mechanisms of the cell, and the superoxides start to lead to a chain reaction of free radical events, and they reach the nucleus where they'll damage the DNA, cause DNA strand breaks. That will activate a DNA repair enzyme called polyadenylyl repair ribose polymerase, and that will then polymerase these adenosine ribose polymers onto glyceraldehyde 3-phosphate dehydrogenase and inhibit that enzyme. Okay, so that's pretty fancy stuff, but the bottom line is it's almost like there's an energy surplus that overwhelms the capacity of the mitochondria. And the reason it happens is because the cell is not able to control how much fat comes in. The fat comes into the skeletal muscle cell faster than does the glucose, and the skeletal muscle cell is unable to regulate it. And that's why I believe we are simply not designed to eat fat in large quantities, and it damages our metabolic system. And then, by the way, because of the insulin resistance, you're now going to have hyperglycemia. And hyperglycemia will lead to the same sequence of events in the cells that are not able to limit the amount of glucose that comes into them. And that's what we just talked about. In the eyes, diabetic retinopathy. In the kidney, diabetic nephropathy. In the peripheral nerves, diabetic neuropathy. And in the arterial endothelial cells, especially like of the foot, for example, and that causes a vasculopathy, a microvasculopathy. And every day I see a bunch of diabetics getting their feet amputated, their lower leg amputated. Okay, so going back to these series of reactions, so what we were just talking about on the previous slide was this enzyme here, glyceraldehyde 3-phosphate dehydrogenase, becomes inhibited. It's through this process of the DNA repair enzyme. Usually they'll write it PARP. Sometimes you can write it PARRP, okay? And once glyceraldehyde 3-phosphate dehydrogenase is inhibited, now everything proximal to that, everything upstream from that will start to accumulate. And first of all, glucose accumulates and then runs this polyol pathway going to sorbitol. And the relevance of that is it'll deplete the NADPH, which is a reducing element used to maintain glutathione in its active form. And so once that's depleted, you now will have a shortage of antioxidants within the cell. This is partly why diabetics are so vulnerable to infections. There's multiple reasons why diabetics are immunosuppressed, but that's a big part of it. The next thing is fructose 6-phosphate is accumulated. It'll then go down a pathway called the hexosamine pathway. All right. Then the next thing, glyceraldehyde 3-phosphate is going to accumulate, again, because nothing can progress down this cycle of glycolysis. So the first thing we'll talk about is some of that will be made in something called methyl glyoxyl, MGO, it's typically abbreviated, and that will lead to the formation of advanced glycation end products. And these AGEs, advanced glycation end products, they'll cause damage inside the cell. They'll then cause damage to the matrix proteins around the cell, in between cells, and they'll also pass out into the extracellular matrix, and then they can interact with the other cells, adjacent cells and whatnot, and they can cause glycation of those cells. So they're very damaging. They can thicken the basement membranes. And so that's this aspect of advanced glycation end products. Now the key point of glyceraldehyde 3-phosphate accumulation is that some of it, it's a 3-carbon molecule, gets made into glycerol phosphate, and then that'll get attached to 2 fatty acids to become diacylglycerol. Acyl just means fatty acid. And this is typically called DAG. Diacylglycerol is called DAG. And then that will activate protein kinase C. And protein kinase C is sort of the master enzyme that just causes all kinds of metabolic problems. So this is sort of continuing from that other slide. Here's our accumulation of diacylglycerol, activating protein kinase C. And then protein kinase C just does a whole bunch of bad stuff. I'm listing here 6 things that it does, and they're all really bad. And this is why, in my opinion, I talk to a lot of diabetics, and in my experience, the majority of diabetics, they're not fully with it cognitively. It's amazing how they have no sense of how sick they are. They routinely will say things. I'll talk to a guy, he's getting amputated, he's going blind, he's in kidney failure. I'm like, yeah, you might want to improve your diet. He's like, oh, at my age, what are you going to do? I'm doing fine. Everything's under control. Yeah, right. To have diabetes is to be very sick from a metabolic point of view. And then the good news is there's almost 0 diabetes in plant-based communities. So the smart move is just look at the epidemiology. It's not that complicated. In low-fat, plant-eating communities, there's close to 0 diabetes. So the smart thing to do is when you see a bunch of people that don't have your disease is imitate them. All right. Well, what does protein kinase C do? First of all, it inhibits endothelial nitric oxide. So nitric oxide is the key vasodilator. You'll hear, Caldwell Esselstyn. He's got the best results for preventing coronary artery atherosclerosis of anyone in the world. And what does he do? He talks about nitric oxide all day long. And why does he do that? Because it's the most important thing to keep the arteries open. So endothelial nitric oxide synthase, that enzyme, is inhibited by protein kinase C. And once that's inhibited, the arteries will, instead of vasodilating, they'll become vasoconstricted. They'll tighten up so they don't deliver blood flow to the tissues as well. In addition, it predisposes the platelets to aggregate. That means to clot. That's bad. You want your arteries open. You know, everybody thinks of bleeding as being a big deal. That's not why people die. The vast majority of people, they die because an artery clots off. An artery in the heart clots off. Myocardial infarction. An artery in the brain clots off. That's a stroke. An artery to the Johnson clots off. That's impotence, okay? It's clotting is the thing to be afraid of, all right? What else does protein kinase C do? It increases endothelin. Endothelin is basically the opposite of nitric oxide. So it's going to cause vasoconstriction of the artery. It's going to cause the platelets to aggregate. And unfortunately, my little webcam image is obscuring the word that was written up here, which is prothrombotic. And what that means is diabetes predisposes to forming blood clots. In addition, there's something called plasminogen activator inhibitor. And when that's increased, you're going to get less fibrinolysis, less ability to dissolve a clot. The bottom line is dialysis predisposes to clotting. And you can see where this is going. Quite often a person is stressed out. Well, that increases the risk of thrombosis as well. You superimpose that on all these diabetic risk factors. And then the person drinks caffeine, a stress equivalent. That will also make them more thrombotic. Then they're sleep deprived. That's a stress equivalent. Make them more prothrombotic. So very quickly, diabetes alone, we got at least 3 chemical mechanisms to become prothrombotic. And then if you triple the stress response with those other things, caffeine, lack of sleep, psychological stress issues, you very quickly have got 6 major contributors to being prothrombotic and have put that person at markedly increased risk for occluding an artery in their heart or their brain or in their foot, for example, and ended up with an amputation. In addition, they occlude arteries in their eye. And they also get something that becomes quite relevant in the eye is called vascular endothelial growth factor, VEGF. That will increase angiogenesis, increase vascular permeability. They'll get these little blood vessels trying to grow into areas that don't have enough oxygen. That's why the vessel growth occurs. And they'll often go blind from this. It's the most common cause of blindness in adults. So it's diabetic retinopathy. And by the way, this could often be dramatically improved. Walter Kempner had all these pictures of the retina before and after he put the patients on a super low-fat rice diet and rice and fruits. And many of them improved their photographs of the retina quite a bit. And that was for hypertension as well as diabetic retinopathy. And they go together. Most diabetics are hypertensive. There's reasons for that we'll talk about. We've actually talked about in other lectures like on hypertension. But the next thing increased by activation of protein kinase C is nuclear factor kappa beta, NFKB. And that is associated with inflammation. In addition, there's increased activation of NADPH oxidase, and that's associated with increased reactive oxygen species, which causes increased oxidative stress. So basically, everything bad. Arteries are clotting off, new capillaries are forming over the macula, fovea areas, causing blindness, leaking tissue into the eyes, causing worsening vision, systemic inflammation, systemic oxidative stress, systemic immune suppression, everything bad. That's why diabetics are very sick, cognitively impaired, and die prematurely. And it's really kind of a silly disease for most people in the sense that if they would just stop eating all this dietary fat, they could dramatically improve. That's been dramatically proven over and over again. I'm always amazed how people aren't willing to just open a book. You know, open a book and read. Take a look at world epidemiology. All you got to do for any disease is type in global distribution of disease. And then if you see an area that doesn't have much of it, ask yourself, why does that area not have much of this disease? And quite often you'll find it comes down to the things we've talked about. The diet, sometimes it's the climate. Okay, human metabolism really only burns 2 things for the most part, under normal conditions, glucose or fat. During starvation, you can burn, ketone bodies. Amino acids are usually going to be converted into glucose. Sometimes they can be converted into other things, but usually into glucose. Alcohol is pretty much just converted into fat. It's like liquid fat. It's been described as that. Fructose almost entirely goes to the liver, and when it's taken, when just in fruits, it comes packaged with all the fiber antioxidants and whatnot. But when it comes like from a liquid sweetened beverage, high fructose corn syrup, you get this giant bolus, and that largely gets made into fat in the liver, and it predisposes to fatty liver. Starch is like a polymer of glucose. Starch, of course, is potatoes, sweet potatoes, rice, beans, quinoa, squash, and that's really like the perfect food, because with starch, the high fiber amount makes it low caloric density. It stretches the stomach, so you get early satisfaction and hunger from the stretching of the stomach. And then the fiber takes a lot of time for the gut to peel it off. So you get this slow, gradual, continuous, prolonged release of glucose into the blood. That's perfect, okay? And the less sweet fruits are fantastic as well. Things like blueberries, for example. Okay, I mean, we got color vision to see fruits when they're ripe. We got hands to pick fruits, okay? Those are things about us consistent with us being like a herbivore. Okay, so that's how starch is great to maintain a relatively normal continuous blood glucose level, only a slight increase relative to most things. We talked about how fat's able to get into the skeletal muscle faster than does glucose, and that's how it causes all the problems, that overnutrition, if you will, and overwhelms the inner mitochondrial membrane electron transport system. How does fat get in so fast? I'm not completely sure. I've tried to look it up a bunch of times. It's actually hard to look up. There are CD36 receptors for saturated fat, things like palmitate, C16, zero double bonds. There's also something called a flip-flop maneuver, whereby a fatty acid can interact with the phospholipid-charged outer component of the plasma membrane bilayer, and then it'll become deprotonated, uncharged, and now it can pass through the hydrophobic, uncharged center of the phospholipid bilayer, and then once it's on the other side, it can then come into the cell. So that's the so-called flip-flop maneuver. And then we talked about CD36 receptors, and there's another transporter mechanism, but I'm not sure about it. It just gets into the cell faster. And again, what it seems to me from studying this a lot is we're simply not designed metabolically to handle large amounts of fat. Okay, we talked about reversal electron transport. We talked about coenzyme Q being overwhelmed. Well, it's really complex 3 that's overwhelmed. It can't pump against that high gradient, so things just back up because of that. Okay, we kind of went through a lot of the stuff about PARP. I always put a little more information into my slides than I do into what I actually talk. So if anybody's interested, you're welcome to look through them in more detail. But that was sort of the key points. We talked about, how do you avoid all this? Minimize your intake of dietary fat. Okay, avoid meat, no oils, not one drop. I recommend avoiding sweets, caffeine, and then watch out for excessive stress, sleep deprivation. Sodium contributes a little bit to insulin resistance. Industrial fructose is bad because it's almost, again, a little bit like a liquid fat because it comes in as a bolus. The liver makes much of that into fat. Exercise a lot. When you walk, that almost does the same thing as having good insulin sensitivity. It sends the glucose type 4 transporters up to the plasma cell membrane so they can allow glucose into the skeletal muscle, and then everything goes well after that. Is diabetes just due to being fat? No, people have a personal fat threshold. And by the way, here's a pretty good book. This guy, I like this guy. He did a good job. His name is Roy Taylor. Roy Taylor is an English diabetes physician and researcher. He actually came out to the United States and trained with Gerald Shulman, MD, PhD. Shulman's like one of the other best researchers in the world. He's a guy that him and his group proved that intramyocellular lipid is the first detectable finding for insulin resistance in diabetics. And then Roy Taylor has some interesting concepts. Like he talks a lot about the concept of a personal fat threshold. And what that means is a lot of diabetics are not that fat. Some people get diabetes at a much lower amount of fat. What he basically says is, if you're one of these people who's just predisposed to insulin resistance, you can't afford to get fat. You might have to maintain your optimal weight from when you were in college, 20 years old, all the rest of your life. And that's actually a normal thing. In most plant-based communities, people weigh about the same when they're 20 as they do when they're 70 or 80. If you're not fat, you got the same height, you're going to weigh about the same. Maybe a little more muscles when you're 20 years old. Anyways, so that's a key point. A lot of diabetics are not that fat. And there's also a lot of fat people who are not that diabetic, but they're not healthy. Being fat, these high BMIs, they've got a lot of problems. And some good warning signs are, if a person is gaining weight, that's a warning sign they're predisposed to diabetes. There's a good chance they're pre-diabetic. If they got fatty liver, if they got elevated liver enzyme, ALT, that's an indicator that they probably have fatty liver. If they're hypertensive, that's another worrisome finding. Okay, and then here's some references. We talked about this fantastic paper, and you can find the video online if you go to diabetes.org. Also down here, the Banting Lecture 2018 by Gerald Sullman. You can find that video online if you seek it out. Really nice book, Pritikin's book. The one from 1979 was my favorite of his books, Pritikin Program. And he goes through a lot of interesting papers on diabetes and other subjects. Here's some of the research studies we talked about, all showing that dietary fat causes insulin resistance, makes diabetes worse. Here's a quote paper just showing that hyperlipidemia causes ischemia. Friedman and Rosenman paper showing that it's not just even sat fat, it's also the other types of oils, the polyunsaturated fats. We've talked previously about the problems of insulin resistance also being caused by omega-3s. And then the Winitz and McKean papers here refer to populations put on to 0.7% fat. That's less than 1% fat, and they did quite well, which reinforces the statement of Pritikin. There's no such thing as a diet that's too low in fat. So a good paper by Shulman too was his mechanisms of insulin resistance. A little bit long, but good detail. The guy's a genius, okay, and he dedicated his whole life to studying diabetes, so he knows a lot. So anyways, hope that's helpful.